Hello everyone, I am going to deliver another lecture on fundamental of welding induced thermal history analysis. In this lecture, I will cover 2-dimensional and 3-dimensional heat flow analysis, and I will also cover different types of cooling rate both in the case of 2-dimensional as well as 3-dimensional case. Apart from these things, I will also discuss in this course about a topic that is related to a very interesting topic that is generally called a dimensionless thickness parameters, which is widely used to predict in which case we should consider 2-dimensional heat source equation or 3-dimensional heat source equation. Why I am going to deliver this lecture in these topics, because the main concern in welding process is the thermal history, that you can say. As the thermal history of a welding structure is the main concern of all aspects related to metallurgy, distortion, what it is called residual stresses. That is why in these topics I will deliver around 4 to 5 different lecture on fundamentals of welding induced thermal history, that is heat flow in welding process. After that I will go to deliver lecture on design and analysis of welded structure. After that I will discuss about the fatigue analysis, which is very important topics related to welding process and welding structure. That related things I will discuss at the end of this course, you can say. So, in today's lecture I am going to deliver the following topics, that is 2-dimensional or 3-dimensional heat flow. Then I will discuss about cooling rate both in the case of thin plate as well as thick plate condition. Then I will go to discuss about the preheat temperature fundamental concept. This preheat temperature related things, more details I will discuss in next lecture. So, we have already got the idea about what it is called, what is the 2-dimensional thermal history of a plate subjected to welding for line heat source. This is for line heat source, I have already told you these things in details I discussed in previous lecture, and this is for generally for point heat source. So, this is generally also called thin plate solution. That means, this is also called Rosenthal thin plate thermal history solution, and this is called also what is called thick plate Rosenthal thick plate solution. So, in which case actually we should consider what it is called 2-dimensional types of thermal analysis, and in which case of a welding process we should consider 3-dimensional types of heat source equation, that we do not know whether you can think whether higher the thickness will provide us the concept of 3-dimensional type or thick plate types of solution, or thin types of plate will give us what it is called the idea about thin plate types of solution. So, because why I am going to discuss this thing, because this is a very important aspects, this you should keep it in mind. What are the aspects you should keep it in mind? That means, only thickness cannot predict, that you can say. Thickness only cannot predict the dimension of the plate. Thickness of the plate, I am writing, that is very important point. On the plate is not able to predict the type of analysis. That means, by seeing the thickness itself you can say that this is for thin plate, this is for thick plate, what I am telling and that means where we should consider a thin plate types of solution, where we should consider a thick plate types of solution. So, that is why what happens, there is required another topics, that is called cooling rate in case of a welding process. So, just I am going to give a example, like I am giving an example, like for a submerged arc welding process, it is observed that for a 50 millimeter thick plate using a current of around 900 ampere and 27 volt welding voltage at a welding speed of 0.2 meter per minute involve essentially a 2-dimensional heat flow. 2-dimensional heat flow means which is based on the line heat source. So, here the plate thickness you can see is a 50 millimeter thickness, whereas for a current of 150 ampere and 20 volt what it is called welding voltage by using a MAG welding process, MAG means metal active gas welding process, that you can say process for a thickness of 20 millimeter thick plate with a welding speed of 0.4 millimeter per minute will cool as if the plate was infinitely thick, what I am telling understand. That means, here the thickness is 20 millimeter, where you are getting a 3-dimensional types of heat flow types of solution, whereas in case of a 50 millimeter thick plates you are getting a what it is called thermal analysis results, which is actually a type of thin plate solution. So, before going to discuss this what it is called thick plate and thin plate types of cooling rate, first and foremost things you need to know, that is generally called type of heat flow in case of a welding process. Generally we can broadly categorize the type of heat flow in case of a welding process into 2 categories, that is generally you can say 2-dimensional types of heat flow, I have already discussed this thing, and 3-dimensional types of heat flow. In case of welding I am just showing, let us consider this is a weld bit in a weld joint. If the heat flow is occur in all direction, that means along horizontal direction, through thickness direction as well as longitudinal direction, all the direction, 3 direction if it will be occur, then this is generally called 3-dimensional types of heat flow. Whereas in 2-dimensional types of heat flow, how it look like, little bit I am showing, already you know. In case of 2-dimensional types of heat flow, generally you can say the heat flow is occur only parallel to each other, that means only in 2-dimensional, what I am telling understand, is the heat flow pattern is, that means through thickness the heat flow is not there, what I am telling understand. So, these types of heat flow is generally considered is 2-dimensional types of heat flow. So, it is observed in this topics you can see for a 20 millimeter thick plate which is showing a 3-dimensional types of heat flow, whereas a 50 millimeter thick plate if which is showing a 2-dimensional types of heat flow. So, thickness of the plate cannot predict the type of heat flow in a welded sample, that you can say. So, that is why, because it is also depends on what? It is also depends on the parameter which we are using in case of welding process. Like you see this current, voltage, welding speed, this is also have a effect on heat flow in a welding process. Okay. So, that is why what happens to predict this concept, that means when we should consider 2-dimensional types of heat flow equation as well as in which case we should use thin plate types of solution. For predicting these things, the concept of cooling rate is very much essential. So, in case of 2-dimensional case, whatever the solution we got for 2-dimensional or thin plate equation, like in previous slide I have shown, from that generally we can derive the what it is called cooling rate along the what it is called heating line, that means y equal to 0. We can write in case of 2 dimensional case, the cooling rate can be written as dt. I am not driving this thing directly, I am writing this cooling rate, that means change of temperature with respect to time is equal to your minus 2 pi k rho c g square V by Q whole square T minus T 0 cube. This is generally called 2 dimensional types of cooling rate. This we obtain using thin plate solution. This you should keep it in mind. Rosenthal thin plate solution, we generally derive this what it is called 2 dimensional cooling rate. And in case of 3 dimensional cooling rate, this become, that means change of temperature with respect to time. Cooling rate means per unit time how much temperature is decreasing, that means whatever the temperature range it is decreasing, that is generally called cooling rate per that means that is generally called cooling rate. Okay. So, in case of 3 dimensional cooling rate, dt by dt you can write as 2 pi k V by Q T minus T 0 to the power whole square. Okay. We derive from using, in previous slide I have already shown, using thick plate solution. So, I am not going to derive these things, this you should keep it in mind. So, from this equation you can observe that the cooling rate is cubically you can say varying in case of thin plate case, whereas the cooling rate in case of a thick plate case it is varying the temperature difference of which is a square in nature. That means you can see from this equation number 2. This is generally called this first equation is called 2 dimensional cooling rate, and this is second equation is called generally 3 dimensional cooling rate. So, I am writing 1 and 2 equation. From this equation you can also observe that the cooling rate is proportional to, you can say cooling rate is proportional to from this equation. So, many things you can observe, it is inversely proportional to Q or 1 by Q. So, 1 by Q is for 3 dimensional case and 1 by Q square is for 2 dimensional case, you can see from this equation. It is also depends on what is called dt by dt, you can say is proportional to V square for 2 dimensional case, and you can say it is proportional to V in case of 3 dimensional case. So, very interesting types of information you can get from here. So, in a particular welding process, depending upon this parameter you can control, you can say the type of cooling rate, because this cooling rate have significant effect on what it is called final microstructure, because all of you are very well familiar about TTT diagram, that is time temperature transformation diagram. There generally you observe that depending upon the cooling rate, generally your final microstructure is means generally generated in a welded structure. Like if your cooling rate is very fast, then what happens, there is a chance of formation of martensite. If the cooling rate is slow, then there is a chance of formation of pearlite or bainite. That types of things you are very well familiar. Then also little bit I will discuss about those things also in this course. So, based on this 2 cooling rate generally cases, what happens, there we developed a very interesting parameter, that is called dimensionless thickness. By this dimensionless thickness, generally we can derive what it is called the concept of when we should use 2 dimensional types of or thin plate types of solution of equation, or when we should consider thick plate types of solution of equation. So, that related thing in subsequent slide I will discuss. So, from the above equation what we observe that increasing that things only I have already discussed, increasing the heat input, that is Q, which reduces the cooling rate, you know, because I have already shown you, and also increase the traverse speed, that is Vx, which increase the cooling rate. I have linearly varying, I have already shown. Similarly, increasing the initial temperature or you can say preheat temperature, because I have already shown dT by dt generally is directly proportional to T minus T0 to the power q for thin plate, or you can say 2 dimensional case, and this is proportional to T minus T0 whole square for 3 dimensional case. That means, for thick plate case generally you can say your cooling rate is lesser than 2 dimensional types of or thin plate case. This you should keep it in mind. And another things also you can observe, if T minus T0, that means if this T0 is high, T0 means is called generally ambient temperature, T0 you can say is called generally ambient temperature, or you can say this is also sometimes if we use some preheating on the weld plate or weld zone, then that is generally called preheat temperature. That is why in combinedly, instead of telling its ambient temperature or preheat temperature, you can consider that is a initial temperature. You see, if this preheat temperature T0 is increased, then you can see your cooling rate dT by dt you can say is decreased. So, by incorporating this preheating effect, you can what happens reduce the cooling rate. This you should keep it in mind. Okay, that is why I will discuss in details, because this is a very important aspect, that means preheating. By this you can control the final microstructure of a welded structure as per your requirement. That is why what happens, this preheating related concept I will discuss in details also. So, what we observe that this T0 if you will increase, then what happens, it reduce the what it is called cooling rate. The cooling rate also you can say I have already shown you in case of 2 dimensional case, this cooling rate generally increases with increase of plate thickness G also. So, I have already told you plate thickness G itself cannot predict the thickness of the plate in the sense whether it is a thick plate or 2 dimensional heat flow or 3 dimensional heat flow. So, it is also generally cooling rate is generally depends on thickness of the plate also. If thickness of the plate high, you can see, because G it is generally I have already shown you in thin plate case, this cooling rate dT by dt is directly proportional to G square. You can see it at the bottom, I have shown this equation, this is the equation. Okay. So, and another things also you can observe from this equation, this cooling rate also depends on what is called material property or thermophysical property, that you can say. You can observe from this equation that this cooling rate is directly proportional to thermal conductivity K. So, higher the thermal conductivity of a material, definitely higher will be the cooling rate, that means rapidly your plate will be cool. This you should keep it in mind. If lower the thermal conductivity of a material, then your what it is called plate or welded plate cool slowly. So, that is why higher the thermal conductivity material like aluminum. So, in case of aluminum generally your cooling rate is high compared to steel, generally steel generally have lower thermal conductivity. What I am telling, understand, because like in case of a aluminum, its thermal conductivity around 10 times higher than steel, that you can say, where in a steel generally the thermal conductivity within a range of around what it is called K is equal to around 50 watt per meter Kelvin. Okay. This you should keep it in mind, because this is a range I am just telling. So, that is why the cooling rate also dependent on what it is called material property also. Now, another things also you should keep it in mind, generally cooling rate also dependent on, like let us consider this is the fusion zone or weld zone. If we generally go further and further distance, that means this is your let us y axis and this is your welding direction is x axis. Okay. So, if we go, if your y is increase, then generally what is called cooling rate generally decrease, this you should keep it in mind. So, that is I have written away from the fusion zone, if we go further and further distance, generally what happens, your cooling rate what it is called decreases, this you should keep it in mind. Some important point I have written here, whatever the cooling rate for 2 dimensional case and 3 dimensional case I have shown, this cooling rate equation is very much accurate, you can say. Once we measure the cooling rate little away from the fusion zone. Little away from the fusion zone means it is near the heat affected zone. In second point I have already written has full form is heat affected zone. Okay. So, here the temperature range generally from melting point to its recrystallization temperature, you know very well. So, in case of steel generally what happens, it is let us 540 degree centigrade to you can say 723 degree centigrade, generally you can consider as per mild steel, generally you can consider the range of heat affected zone temperature. Say within this range generally you can say your microstructural changes is occurs. This heat affected zone microstructure generally you can say highly depends on what, this cooling rate, you know. I will just discuss in next slide little bit more details about this. So, this that is why what happens, this equation for 2 dimensional 3 dimensional cool range is very accurate in case of a temperature range which is lower than its melting point temperature. This equation is very accurate, it is observed experimentally also. And also it is observed, you know, that generally cooling rate in case of a fusion line or central line of a welding process is around 10% higher than heat affected zone cooling rate. That is why what happens, whatever the equation I told you for cooling rate calculation, this equation is very much accurate for what it is called welded structure, that you can say. And another things you should keep it in case of structural steel, as the majority of the what is called microstructural changes is occur in the heat affected zone, which is away from the weld central line zone. That is why what happens in case of steel structure, this cooling rate equation is very much accurate. Now, why I am discussing this cooling rate more and more, why I am discussing cooling rate related things in detail in this course, because this cooling rate is the one of the very important aspect for deciding the final microstructure of a welded joint. All of you are very well familiar, due to this high intensity heat and melting of the weld zone, what happens, and due to this non-uniform expansion contraction, due to this cooling and what it is called heating process, there are different changes occur. There are different types of defect generally developed in case of a welded structure. That defect can be what it is called, you know, there are so many defects generally are there in a welding process. So, some of the defects is related to metallurgical defects, some of the defects are related to what is called stresses, that means weld induced residual stresses. Some of the defect you can consider as a weld induced residual deformation. So, these are the things generally developed due to this thermal effect of a welding process only. Now, the final microstructure which affect the weld quality, you can say one of the most important topics related to welding. For understanding that topics generally, this cooling rate and this TTT diagram is very much essential. So, this is generally TTT diagram. What is the full form of TTT? You know these things. This is time, temperature, transformation diagram. So, time, temperature, transformation diagram is a very important diagram for predicting, you can say, the final microstructure of a heat treatment or welding process, that you can say. Generally this TTT diagram, this left side curve of this TTT diagram is called start of transformation. You know this thing very well, then also little bit, and this is called end of transformation. This right side curve is called end of transformation curve. Now, all of we are very well familiar that generally TTT diagram or cooling, generally you know cooling rate is important below the recrystallization temperature, or you can say a lower critical temperature. This is called lower critical temperature. You know this above the lower critical temperature, the in case of plain carbon steel, you can say this is especially I am discussing about a plain carbon steel TTT diagram, you can say. Here the above recrystallization temperature, generally you can say austenite phase is there, you know. Austenite phase, what is austenite phase? You know very well. It is a generally in a interstitial solid solution of carbon in gamma iron. What I am telling, understand? So, here there is a solid solution of carbon in gamma iron. Gamma iron, what is gamma iron? You know gamma iron generally is a FCC, face center cubic types of crystal structure, you know very well. So, it generally permitting high solubility of carbon. This austenite can contain a carbon solubility up to a range of, you know, from iron carbon diagram is around 2.06% at a temperature of 1147 degree centigrade. That is generally higher critical temperature. This austenite phase generally crystal structure, it can permits maximum what is called 2.06% of carbon solubility at a temperature of 1147 degree centigrade. So, austenite generally does not exist where one is generally crossing what is called, once it crossing, you can say this lower critical temperature. Generally above the higher critical temperature, this what is called austenite, little bit here I am writing here, generally austenite structure is here, generally austenite structure is stable, but once it cross, you can say once it cross this line, generally then austenite structure become unstable. What I am telling, understand? Now, with time, once it cross this lower critical temperature, after that once it once the time increase in this zone, then what happens, that structural, that means that austenite start changing its microstructure. What I am telling, understand? Changing its microstructure means changing its phases, you can say. So, that phases depends on, generally you can see here I have already shown you, in between there is a, generally in between these two curves, starting and end curve, you see there is generally what it is called at the you see, first of all I want to define, there is a nose of this curve, there is a nose of this curve, this nose of this curve temperature is around 500, around some book it is written as 540, some book it is written as 550 degree centigrade temperature, at around 550 let us consider. Okay. So, 500, this nose temperature is around 550 degree centigrade temperature of this starting of this transformation curve. So, above this dotted line you can see the structure is you see this structure is generally in left side of this curve, the structure is gamma. So, in between generally is a mixture of gamma plus pearlite, P represent pearlite, and the end of this transformation curve, rest of the austenite is transformed to pearlite. If a cooling process is taken place, let us consider this way the cooling process is taken place. Okay. if the cooling process is taken place like this, then what should be its final microstructure? That means, at the starting of the what is called austenite, it is passing through what is called gamma plus perlite. Generally austenite is start converting what is called perlite, and this dot in between generally there is a dotted curved line is there. This is generally you can consider as 50% transformation line. This you can consider as 50% transformation line. So, you see generally once this cooling process pass through this curve, generally this gamma phase start converting to other phase. Like if it is above the middle or nose line of this TTT diagram, then generally this gamma gradually start to form perlite. What I am telling, understand? That means, if it is come in middle of this TTT diagram, then here you can say middle of this TTT diagram 50% austenite, that means 50% austenite will be converted to. So, in this location of your material there will be 50% gamma plus 50% perlite. So, if it pass again further to end of this what it is called transformation or TTT diagram, here you can say your what it is called 100% perlite structure will form. That means, austenite is unstable, I have already told you it is unstable phase below recrystallization temperature. That is why with time generally what happen is you start transforming. Okay. This you should keep it in mind. So, these types of cooling where generally we can get what it is called perlite types of a structure. So, these types of cooling generally you can get either by air cooling or by furnace cooling. What I am telling, understand? Like in case of furnace types of cooling, little bit I am writing these things, you can get fully what is called perlitic types of structure, I have already written, but here generally cooling rate is, you can say cooling rate is very is slow. What I am telling, understand, very slow. Here you can see like what happens, this nose of the generally nose of the cooling rate time is around 1 second, whereas at nose location the cooling rate time is around 10 second. What I am telling, understand, this you can say. Now, if your cooling rate is rapid, like what happens, let us you want in your final structure should be martensitic types of a structure. So, if your cooling rate is like you see here I am just showing, if your cooling rate is like this, then what happens, you can get a fully martensitic types of structure, or you can your cooling rate can be like this also. So, let us consider this is curve A and let this is a curve B. Here little bit I am discussing more details, what is this A curve and what is this B curve. Generally A curve has a very interesting name, that is called, you can say, critical cooling rate curve. What I am telling, understand, critical cooling rate curve, you can say. Why it is called critical cooling rate curve? Because this is a cooling process. If your means welded structure is subjected to cooling like this types of line, that is line A or curve A, then what happens, your final structure will be, you see here I have already shown you, this is generally called martensitic strut, M represent martensitic strut what it is called strut line, and this M 50% means martensitic, that means austenite convert to 50% martensite, and F M 90% means 90% martensitic transformation is already taken place. So, you can observe what is the temperature range. So, martensitic starting temperature range is within a range of around 220 degree centigrade. What I am telling, understand. So, you see, so once your austenite start crossing this martensitic line, then what happens? It start transforming to what it is called martensite. So, this is line A is the critical cooling rate line. Here you can say 100% martensite will be formed. 100% martensite will be formed, but this martensite will have, you can say, less deformed. Yeah, whereas in case of B curve, here also you will get 100% martensite, but that martensite generally is more deformed and it is generally, you can say, generally more harder than what is called martensite in case of cooling curve A, and it will also produce more residual stress in case of a welded structure, that you can say. The generally very rapid cooling is occur in case of water types of quenching process. These types of curve B can be what is called wild types of quenching process or wild cooling process, you can say. So, you got the idea what is the impact of what is called different types of cooling process on final structure. So, you got the idea about what is critical cooling curve. Okay. Critical cooling curve means less distorted and less internal stresses compared to cooling curve B, though both the microstructure have what is called final microstructure is have martensitic types of characteristics, but what happens, you can see your final structure generally have different types of stresses as well as distortion. This you should keep it in mind. That means gamma start transforming. One thing you should keep it in mind, at the starting line generally your 100% austenite is there. Once this austenite just cross this starting line, then this austenite start converting to other phase. Once this austenite start converting to other phase, that phase is, you can say, is a permanent phase in this lower critical range. You should keep this thing in mind. Once it form, that will remain there. So, rest of the you can say rest of the gamma will then transform to other phase. Like here I want to show one curve, that is curve E, you can see, that is curve V here I have shown. In this curve, like here you see, first it start transforming, after that it pass the what is called nose of the 50% nose of the dotted curve. So, here generally you can say 50% gamma phase transform to pearlite, rest of the 50% generally it passed into the what is called, is passed into the bainite region. So, rest 50% generally once it passed in bainite region, rest 50% is converted to another 50% bainite structure. So, these curves will provide a 50% pearlite plus 50% bainite structure. So, these types of process is generally called interrupted cooling process. So, where what we used to do here, generally there is a first rapid cooling, after that generally we soaked it in a salt solution. So, this is generally for a constant temperature, after that generally we can further cool it by to room temperature. Okay. This is generally called a interrupted cooling process. This has also a very important application. Let us, in some cases you want the combination of pearlite or bainite structure, combination of pearlite or martensitic structure, then what happens, you need to use these types of cooling process. Okay. Now, why I am discussing this thing? Because whatever the cooling rate I have shown from this diagram, you can get a very interesting idea, because here with time, that means for a cooling process from 723 degree centigrade to room temperature, let us around 25 degree centigrade temperature. Okay. Within this temperature, what should be the time for a welding process? That generally predict the final microstructure of your what is called final microstructure of your welded specimen. This you should keep it in mind. So, this cooling rate means here you can see if the cooling rate is very high, cooling rate is very high means per second, if the cooling rate is let us 100, then what happen, it is called rapid cooling. If the cooling rate is slow, then that means per second less amount of temperature is decreasing, that means what I am telling, understand, then there your cooling rate is called generally slow cooling rate. So, based on this time temperature diagram, you can decide what should be your cooling time from 723 degree centigrade to you can say room temperature. This you should keep it in mind. This is generally decide the final microstructure of a plain carbon steel, which I am showing here. Okay.